What if we could go back in time to a time when our planet was unrecognizable? What would we discover if we traveled 1 billion years into the past? Dear traveler, welcome. Today we're going to explore time. Imagine a world where oxygen is just beginning to accumulate in the atmosphere. A primitive Earth where the continents, still young, drift on an orange-red ocean. No plants, no animals, just colonies of bacteria that carpet the seabed and color the shallow waters. Volcanoes spew lava in a stifling atmosphere. But before you set off on your next adventure, make sure you like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! The further we go back in time, the more life seems to struggle to hatch. From simple bacteria to human beings, giraffes, eagles and turtles, there have been millions of years of evolution. Each link in the chain has its own importance, leading to today's rich and luxuriant biodiversity. One of the pivotal stages in this evolution is right on the geological timescale we're currently on, the Proterozoic. It's in the very last era of this eon, the Neoproterozoic, that we're going to take a look at the world from the perspective of 1 billion years. Proterozoic means before the animal in Greek. Given what we knew just a few decades ago, the period was aptly named. Today, however, we know that this was far from the case. The first animals were already present in the Proterozoic, at least in its last period, the Neoproterozoic. The Proterozoic never ceases to amaze us. Every year, through studies carried out on the subject, we go from surprise to surprise. Our knowledge and increasingly sophisticated technical and technological resources enable us to support our hypotheses and gain a better understanding of the world before. 1 billion years ago, life was in its infancy. We're now in the third part of the Proterozoic, which includes the Paleoproterozoic, the Mesoproterozoic, and finally, the one we're particularly interested in this video, the Neoproterozoic, i.e. the 500 million years before the Cambrian. Prior to the Neoproterozoic, the only visible life forms were microscopic but resilient bacteria and archaea. These organisms were masters of survival, capable of adapting to extreme conditions. It has to be said that until now there wasn't much to eat. And even if there had been, it would still have been necessary to have teeth. And yet, despite the harshness of the environment and the scarcity of apparent sources of nutrition, life is hatching and seems stable. So stable, in fact, that it developed and diversified. Let's take a look at the twilight of the Mesoproterozoic, just before it ended and gave way to the next era, to better understand the evolution of the living world and its impact on the environment. Among the most remarkable of these early life forms are cyanobacteria, organisms that played a key role in the creation of our atmosphere as we know it today. Their importance in the past is well known, and we are able to date their appearance on Earth thanks in particular to the stromatolites they left us, which we discovered billions of years later. Stromatolites are fossil rocks of biological origin. The oldest dates back over 3.4 billion years. They dominated marine life throughout the Precambrian period, from around 3.5 billion years ago to 500 million years ago. Even today, colonies of cyanobacteria can be found creating reefs of stromatolites, limestone, and sometimes silica, notably in Australia's Yalgorop National Park. We'll have more to say on why shortly, but you can already tell that these little creatures produce oxygen. They're also known as chlorophyll bacteria. In other words, they are slowly beginning to oxygenate the atmosphere, a real upheaval for the planet. A necessary upheaval, because without it, biodiversity in the living world as we know it today would never have existed. At the origin of all possibilities, a tiny little bacterium. Incredible, isn't it? During most of the Proterozoic, it's true that the first living organisms remained unicellular and fairly elementary, limited to bacteria and cyanobacteria. However, towards the end of the Proterozoic in the Neoproterozoic, contrary to what one might think, life took a new turn. The complex organism finally enters the scene. Here we are at last, 1 billion years, the Neoproterozoic. Most life forms remain unicellular at the end of this period, but multicellular organisms are timidly appearing. That said, multicellular organisms dating back 2.1 billion years have already been discovered. As you can imagine, it took millions of years for the different organisms of the time to adapt and change their genetic code to allow for this major evolution. The formation of a nucleus or cell specialization. This cellular diversity will enable new organisms to emerge, creating by extension new ecological niches, and thus a whole ecosystem in the making. Among simple organisms, we can already see diversification taking place in algae, for example. These first steps towards complexity will pave the way for other forms of life, closely linked to their presence. The butterfly effect, or domino effect, whatever you want to call it, takes on its full meaning here. New species lead to new niches, and these niches in turn lead to new species, until a veritable ecosystem is established. An ecosystem in which all species and their environment are closely linked. It is the richness of this new ecosystem that will encourage the arrival of new, more evolved organisms in the following eons. During the Tonian, the first period of the Neoproterozoic, which stretches from 1 billion years ago to around 720 million years ago, a number of microfossils have been found that enable scientists to understand this crucial stage in our planet's history. This is the first evolutionary radiation, if we can put it that way, of acritarchs, beings that we are unable to classify in any particular biological family. Evidence of the sexual reproduction of fungi and green algae can be found in Australia. Vertical burrows were also found on Australian soil 800 million years ago. The scientific community that has studied these burrows believes they are probably the work of vermifores akin to pogonophores, i.e., annelid worms. Other, more complex life forms appeared during the second half of the Neoproterozoic, the Cryogenian. This period is named after the period of glaciation that our planet underwent. While the algal population is on the rise, some scientists believe they have uncovered other primitive life forms living at the time, notably sponges. These sponges, through their mineral production, began to compose numerous marine rocks, such as spiculites, gazes, and spongolites, and thus enrich their environment on their own scale. From then on, other complex organisms would emerge one by one to complete this large family of aquatic fauna at the end of the Precambrian. This is a pivotal period between the bacterial world, then the algobacterial world, and finally a truly eukaryotic world with much more complex living organisms. But to meet them, you'll have to wait a little longer. I promise these animals will be part of the journey, but we've got a few steps to complete before that famous encounter. How did these animals manage to settle on Earth? Under what circumstances? What evolutions did they adopt? What difficulties did they face? Let's go back to the dawn of the Tonian, the first period of the Neoproterozoic. To understand the changes taking place in the living world, we first need to take a closer look at the environment in which these beings evolved. Back then, the Earth was not divided into 7 continents as it is today. Everything was different, because since the very birth of the Earth, its entire surface has been in eternal motion. Imagine a giant jigsaw puzzle, where the pieces are still moving today. This is what the tectonic plates that cover the surface of our blue planet finally look like. If I say single continent, the first idea that comes to mind is probably Pangaea. It's true that it's the most popular single continent, no doubt because it's linked in our minds to the dinosaurs, the emblematic animals of our past. However, our planet has seen many other significant events than Pangaea and dinosaurs in its lifetime. Plate tectonics are thought to date back over 4 billion years. During this time, plate movements have regularly brought about changes on our planet. The continental waltz has played its part more than once in our history. The continental masses have sometimes moved closer together, sometimes further apart, as plate tectonics has done. 7 times in Earth's history, to be precise, if we count the 7 supercontinents our planet has known. The 4th supercontinent, Columbia, is thought to have formed between 1.8 and 1.5 billion years ago. Little is known about this supercontinent. The remnants of this distant past have not withstood the hundreds of millions of years that followed. There are still too few clues to understand with any certainty this pivotal stage in the life of the Earth. We do know, however, that a few tens of millions of years later, Columbia fragmented, then the landmasses, like magnets, attracted each other again to form the first well-documented supercontinent, Rodinia. According to the researchers who studied this particular era, this supercontinent was made up of various cratons, including the North American craton, known in scientific jargon as Laurentia, as well as the Eastern European craton, known as Baltica. Other cratons include the Amazon, West Africa, and Australia. After its disintegration, a new continent was born millions of years later. The supercontinent Pannotia, also known as Gondwanaland or Pan-Africa, was born. The name says it all, as the African cratons occupy a central place on this supercontinent. The last supercontinent is the best known of all, because it is the closest to us in time. It is perfectly documented and closely linked to animals that are popular despite their disappearance. Dinosaurs have always fascinated us. The unique continent linked to these animals from another age is, of course, Pangaea. It was formed around 335 million years ago and broke up during the Jurassic period around 175 million years ago. Now that you've learned a little more about the different ways in which the Earth and supercontinents have come together, let's get back to the one we're interested in now, Rodinia. This supercontinent was formed during the Neoproterozoic. Between 1.1 and 0.9 billion years ago, the land masses came together to form a single space. Scientists gave it the name Rodinia, Russian for homeland, birthplace. Located 60 degrees north latitude to the South Pole, this unique land has an average temperature of 10.5 degrees Celsius, or 51 degrees Fahrenheit. It is surrounded by a vast ocean known as Moravia. If life seems possible in this water, on land it's quite another matter. Between dust, desert, and rocky chaos, it's hard to settle in. The first thing that strikes you is the lack of vegetation. If this kind of desert is still present today in some parts of the world, you have to imagine that at the time this type of landscape covered almost the entire landmass. On the coasts, a few changes are in the offing, but we're still a long way from being able to welcome plants miles from the shore. Life remains exclusively aquatic. So for the time being, everything takes place under the world's waters. Oceans and seas cover a large part of the planet and will play a major role in the geological changes to come. They are the environment in which the first oxygen-generating organisms develop, and in which many species will diversify and grow. But this movement of plates will also have consequences on the surface, and become one of the first challenges that these beginnings of life will have to face. Plate tectonics were very active during the Proterozoic. This internal activity inevitably had numerous consequences on the surface. It led to the construction of a number of major mountain ranges. These are known as orogenies. During this period, there were several orogenies. 1 billion years ago, the period we're interested in here, falls between two major orogenies. The first is the Grenvillian orogeny, formed between the breakup of Columbia and the formation of Rodinia. The next will take place several million years later, at the very end of the Neoproterozoic, with the formation of the Cadomian and Pan-African mountain ranges. In addition to the formation of mountain ranges, volcanic eruptions are numerous. The Earth's internal activity is intense. The fiery heat and accumulated energy must be evacuated to some extent. Otherwise, our planet would not be able to withstand such pressure for very long. The period is thus punctuated by the dance of plates, volcanic eruptions, and mountain building. While the landscape is already changing, with the appearance of monuments of Earth that seem capable of touching the sky, the supercontinent Rodinia is already gradually disappearing. Volcanism and continental shifts continue to reshape the planet's surface, influencing its geography. The face of the Earth is changing. New mountain ranges form, oceans modify, and vast expanses of land slowly emerge. Rodinia is breaking up. It will gradually separate into 8 distinct pieces of the same puzzle. These visible movements of the Earth's crust bear witness to the Earth's inner turmoil. Deep-seated rocks deform and become a viscous fluid, carrying the excess heat of our blue planet. Crustal displacements, i.e. of the Earth's crust, follow the movement of this fiery fluid. The rupture of Rodinia will bring about the birth of another element. There's a place on Earth that makes many of us dream, and it didn't exist at the time: the Pacific. Rodinia first splits into 2 continental masses. On one side, Australia and East Antarctica, on the other, Laurentia, with North America and Greenland. Between the two, a rift. A collapse trough echoing the fracture of the Earth's crust may have existed a little earlier. In this rift, we find volcanic activity. It was gradually invaded by the sea, the rift becoming an oceanic ridge. This sea is none other than the Pacific. Well, the Panthalassa, of which the Pacific is a part. We could also speak of the Proto-Pacific. The Panthalassa, the preferred term when referring to Pangaea, comprises the Pacific Ocean and the Tethys, a gulf that extends into Pangaea, the next supercontinent to come. The ocean that formed between Australia, Antarctica, and North America is therefore made up of the famous Pacific Ocean. The Pacific Ocean is one of the most beautiful oceans on Earth. 1 billion years ago, we were at a turning point, just after the Great Oxygenation. It may look like good news on paper, but for organisms used to living without it, it was a terrible ordeal. While for some living beings this new gas and quantity is synonymous with chaos, for others it means the possibility of renewal and exceptional diversity. Let's go back a few million years to better understand this new feature of our planet. Shortly after its formation, the Earth already had an atmosphere, but it didn't have quite the same characteristics as today. In fact, we speak of a primitive atmosphere. 4.6 billion years ago, this primitive atmosphere was made up of carbon dioxide, dinitrogen, and water vapor. How can we know what these atmospheric elements were and be certain of their presence 4.6 billion years ago? It's not always easy to date an animal or plant trace, so a simple gas? How can it be? 4.6 billion years. That's a long time when you think about it. With so many zeros, it's a number that's almost impossible for our brains to represent. So much has happened in all that time, and yet, the study of fossils, in particular gas bubbles and zircons, those highly resistant minerals that have managed to brave one millennium after another, will be invaluable witnesses. They tell us the story of a time long ago, and with the right knowledge and tools they can shed light on it. We now know with certainty the composition of the primitive atmosphere. Carbon dioxide, nitrogen, water vapor. Everything could have stayed the same, but one little grain of sand in the gears and everything falls apart. While the consequences may be devastating for some, it's a real boon for others. The primitive Earth cools over time. Water vapor liquefied, helping to form oceans and rivers. Around 3.5 billion years ago, as you already know, life began to appear in water, notably with the arrival of cyanobacteria. Cyanobacteria will be at the origin of many things and will turn the established order upside down. With the oxygenation of the ocean and atmosphere, these two environments become oxidizing, a characteristic they didn't have before. Initially, the production of oxygen by bacteria, autotrophic prokaryotes, reacts with reducing compounds present on the surface. These reducing compounds are methane, salts, and iron minerals, also known as oxygen sinks. After several million years, all these substances have been oxidized and no longer act as oxygen sinks. They are said to have reached saturation point. This time, we're talking about 2.45 and 1.85 billion years ago. Oxygen is then released into water, on Earth and in the atmosphere, always in small quantities. In the aftermath of this great oxygenation, the atmosphere becomes critical for anaerobic prokaryotes. It's as if their own environment becomes toxic for them. Imagine running out of air every time you breathe in, suffocating, searching tirelessly for the gas that connects you to life, without succeeding. Bacteria release this suffocating gas. It is consumed in turn through the formation of oxide, i.e. rust. This encounter leads to a number of reactions, including oxidation and the formation of iron ribbons. Why are we talking about rust here? Because of the landscapes that you can still admire on Earth today, and which serve as our witness. Look closely at these places steeped in history. You see these long reddish-brown bands? Well, they're geological evidence of our past. These alternating red and gray layers are known as banded irons. 2 billion years ago, when rust was produced, it fell gently to the bottom of the water, covering the seabed.
traces that we can still detect today, enabling us to date events such as when oxygen was found in abundance on Earth. Iron, Fe2+, soluble in water and derived from continental erosion, reacts in contact with oxygen, transforming into Fe3+, not soluble in water this time. It's this ancient seabed that you see here in Michigan in the USA, but it's also found in Australia, Brazil, India, Russia, and South Africa, for example. These are also known as paleosols or fossil soils. Here, the paleosols you see in this part of the world were formed by rock weathering, i.e., the erosion of continental rocks in contact with the atmosphere or water. Their distinctive red color is due to the presence of hematite, an iron oxide mineral with a chemical formula Fe2O3. This formula will help you understand the link between iron and oxygen. In the sea, you'll find alternating red and gray layers, the grays corresponding not to iron precipitation, but to silica. Between 1.85 and 0.85 million years ago, the Neoproterozoic period we're currently in, the oceans are still releasing oxygen. It is absorbed by the land, but also enters our atmosphere. One of the most significant events of the period, along with the arrival of eukaryotes, was the formation of the ozone layer. We leave the ocean for the atmosphere, where oxygen takes on a whole new dimension. It's called trioxygen, or more commonly, ozone. Ozone is in fact a chemical substance composed of 3 oxygen atoms. The special feature of this molecule at high altitude is its capacity to absorb ultraviolet solar radiation. These rays are the most dangerous for the body. This ozone layer thus becomes a real blessing for future living beings and ecosystems. If the sun is a blessing for its heat and light, it can also be deadly for living organisms. There are 3 types of UV radiation. These are UVA, UVB, and UVC. UV radiation causes mutations in DNA, even denaturing the molecule, which is why it is so dangerous. The ozone layer found in the stratosphere forms a sort of protective blanket. It is capable of absorbing all UVC rays, as well as some UVA and UVB. Thanks to it, the genetic material of living organisms is protected. The Neoproterozoic is a pivotal period, even if the Great Oxygenation took place a few million years earlier, thanks to its high oxygen content. It marks a break between the first Proterozoic eras, the Paleoproterozoic and Mesoproterozoic, and the last era, the Neoproterozoic. Oxygen was therefore the dominant element 1 billion years ago. If we analyze oxygen concentration by estimating its partial pressure, we see that the pressure is 0 until around 2.4 billion years ago. Then, between 2.4 and 1 billion years ago, the partial pressure of oxygen is less than 0.1 atm. Then, shortly after 1 billion years, between 900 and 800 million years ago, the pressure peaks at over 0.3 atm. This changing atmosphere brought with it new climatic conditions. With a methane-saturated atmosphere, the Earth was initially much warmer than it is today. Imagine tropical temperatures and warm seas bathed in light, creating an environment conducive to the first steps of life. Despite this rather calm climate, which was conducive to life, we mustn't believe that everything was simple, and even less so that the elements were stable. If this era was indeed marked by heat, ice ages also took place. The Earth was then entirely covered in ice, a phenomenon known as Snowball Earth. This kind of event is indicative of a great deal of internal activity. Indeed, during the Neoproterozoic era, continental displacements were known to be intense and complex. Rodinia probably fragmented into 8 separate pieces of land. Of course, such fragmentation is not without consequences. The various ice ages are undoubtedly closely linked to this dislocation of the continent. To better understand what is at stake in the so-called snowball effect, we need to understand its mechanism. How can the Earth merge into such a mantle of ice? How can it cover almost the entire landscape? Forest, ocean, desert. Everything seems to be buried under snow. It's important to understand that if living beings occupy the land, the ocean, or even the air, it's in the atmosphere that we find one of the keys to making life possible. It's not the only one, but it's one of the links in the chain. The atmosphere affects the quality of the environment, protection from radiation, and climate. Climate is closely linked to the Earth's radiation balance, i.e., the difference or balance between the energy received by the sun and that reflected back into space by the oceans, land, and of course the atmosphere. A balance exists when the rate of greenhouse gases produced is close enough to that absorbed by the sinks that remove them from the atmosphere. However, as we have already seen, the sudden arrival of oxygen will completely upset the established order and have multiple consequences, both on the composition of the atmosphere and on the oxygen content of the ocean. From then on, this seemingly insignificant change will shake up the entire planet. These upheavals in the ocean have effects in the atmosphere. As we saw earlier, certain gases are transformed when they come into contact with the atmosphere. This is the case for oxygen and ozone, for example. What we haven't yet discussed in detail is that this is also the case with methane. Methane reacts with oxygen to produce carbon dioxide, a less potent greenhouse gas. The planet begins to cool. Little by little, the planet is covered in ice. Thick ice, sometimes kilometers deep, covering the entire planet. Seen from the sky, the Earth is unrecognizable. Methane gas is falling, and so are temperatures. And it's far from over yet, since ice is appearing as a result of these drastic falls, and the phenomenon is set to become even more pronounced. To understand this, we need to understand the albedo effect. Albedo is the ability of a celestial body to reflect the sun's rays back into space. As planet Earth becomes increasingly icy, and ice is a highly reflective material, temperatures continue to plummet to the point where for several million years, our planet is nothing more than a vast snowball gravitating around the sun. This is not the Earth's first ice age. During the Proterozoic, the Earth experienced 4 supercontinents, as well as 3 major ice ages, making for an eventful period of upheaval. There was a major period of glaciation in the Paleoproterozoic, from around 2.4 billion years ago to 2.1 billion years ago, during the first Proterozoic era. Following this period came the first orogeny, the Hudsonian orogeny. During the Neoproterozoic, the last era of the Proterozoic, the Earth underwent 2 successive major glaciations, as well as others of lesser importance. The first major glaciation was the so-called Sturtian glaciation. It was a worldwide glaciation known as a global glaciation. It took place in the Cryogenian period and is estimated to have spanned some 57 million years, between 717 and 660 million years ago. Other glaciations took place before and after it, but this one was undoubtedly more impressive than the others, both in terms of intensity and duration. The same is true of the Merino glaciation, which came a few million years later, still in the Cryogenian period. It lasted from 650 to 635 million years. Although shorter in duration, it was nonetheless very intense. Once again, ice affected almost the entire planet. Depending on the region, the world's waters can be ice-covered to a depth of several kilometers. When scientists study the glacial deposits of the period, they estimate that it is perhaps the most intense in our planet's history. But what kind of events could put an end to this downward spiral of glaciation? The answer lies not only in the bowels of the Earth, but also in the air. The greenhouse effect will be the only possible mechanism for halting the glaciation process. The Earth's greenhouse effect is triggered by the accumulation of carbon dioxide produced by volcanoes, but also by the release of methane. Once the process is underway, the greenhouse effect works the Earth over. Ice melts slowly but surely. Gradually, after millions of years of toil, milder temperatures finally return, more conducive to life on land and at sea. Erupting volcanoes, intense internal activity, escaping gases. There's a good reason for all this. Under the Earth there's movement. Lots of movement. Once the Earth has cooled down, the famous snowball, our planet will shed its icy mantle and return to milder temperatures. As a result, the snow and glaciers will melt, bringing with them new nutrients into the ocean. These combined events encourage the expansion of new species into a newly hatched ecological niche. Although life is still exclusively aquatic, after a period of oxygenation of the oceanic environment, followed by a period of significant cooling, we see the appearance and development of a number of living organisms, such as algae, sponges, and gaboniontes. These gaboniontes lived 2 billion years ago. They remain macroscopic, but are still part of the multicellular group. However, they are not eukaryotes. They have a sort of pleated skirt around a central ring. Their tissues are soft or gelatinous, rather like those of jellyfish, for example. Several species of these gaboniontes already existed at the time. By studying the rocky sediments, we can see that these organisms were undoubtedly able to move in this fossilized substrate. The possibility of the multicellular organism also leaves room for specificities and a great possibility of diversification. Although scientists believe it unlikely that the gaboniontes left descendants, a few 100 million years later, between 1.7 and 1.2 billion years ago, we find the presence of new multicellular organisms, the red algae. These red algae appeared after the so-called blue-green algae, i.e. cyanobacteria. The oldest known red algae was found in India's Vindhya mountain range and dates back 1.7 billion years. These red algae, part of the rhodophyte group, took advantage of the new conditions imposed by cyanobacteria, oxygenation. Although life is developing, it remains a constant struggle. No major predator in sight to be sure, but the environment remains hostile enough to restrict development conditions. Our red algae, for example, have to contend with a lack of light and ever-increasing oxygen molecules in the ocean. They therefore choose to move a little closer to the surface, to adapt to these new conditions and take advantage of the sun, too. This is made possible by the ozone layer, which, as we saw a few minutes ago, protects living organisms from the sun's ultraviolet rays. Even so, algae cannot count on energy autonomy based solely on the production of chlorophyll through photosynthesis. Although they occupy a little more of the surface, they still remain at great depths. They therefore compensate for the difficulties inherent in their dark environment by using complementary pigments to capture other light frequencies from the sun's rays. These red algae are in fact equipped with pink protein pigments. It is these pink pigments that enable them to capture the sun's energy and manufacture organic matter during the process of photosynthesis. In addition to algae, this period also saw the arrival of new, more complex and diverse organisms. The diversification of life seems to have really begun. After new algae and gaboniontes of all kinds, the first metazoans are now making their mark in the ocean. In these new creatures, which could be considered the first animals, properly speaking, to be called metazoans, there are a number of significant changes. The first is the constitution of several differentiated cells that form tissues. Then there's the nucleus and mitochondria. All this represents a major evolution in the living world. And then there's the fact that they are heterotrophs, i.e., they feed on organic matter. The first known metazoan is undoubtedly the sponge. Researchers have found steroids, a particular group of lipids, dating back some 890 million years. In the sponge, everything seems to be organized to filter water, even though there are as yet no well-defined organs or tissues. The sponge's entire body serves as a filtration system for its own nourishment. Water penetrates ever finer canals, some serving as distributors, others as collectors. In biology, this is known as the aquifer system. The sponge is thus able to feed on particles, notably bacteria, through each of these channels and thus through its cells. This is what we call a phagocyte, or more commonly an eating cell, and its capacity for phagocytosis. The phagocyte, by simple physical contact, ingests the target particle, less than 0.5 microns in size, then rejects the waste products of this nutritive process through the same channels. To support this entire nutrient system, a hard, stable body is needed. This is provided by the skeleton, a corpuscle made of silica or limestone in the sponge family. In our oldest species, we find calcite ramifications, rather like microbranches forming a limestone protein skeleton. While the age of this ancient sponge has long been estimated at around 650 million years, it may be that we need to put back its birth by almost 200 million years. Professor Elizabeth Turner of Laurentian University in Canada has made an incredible discovery in stromatolites. These stromatolites are formed by photosynthetic bacteria. They are found in the Pilbara region of Australia. Inside is pyrite, a mineral composed of nitrogenous organic matter produced by bacteria. It's in this type of stromatolite that traces of a sponge have been found, at least its skeleton, and ramifications showing a worm-like organism living inside. Not a worm, but a sponge. Its body is mineralized, and the spongin is decomposed, revealing the network of tiny canals we mentioned earlier. What's incredible about this discovery is, on the one hand, its dating. In fact, the sponge is estimated to be no less than 890 million years old, which puts the age of previous estimates back by more than 200 million years. Secondly, it shows that they could have lived close to the cyanobacteria responsible for the creation of stromatolite. Finally, we mustn't forget that oxygen in quantity appeared much later, and that between 635 and 720 million years ago, the Earth underwent a period of global glaciation. This means two things. Firstly, that oxygen was not solely responsible for the development of Metazoan life. And secondly, that life was already sufficiently adapted and robust to survive the Snowball Earth. Although the various ice ages that followed would undoubtedly lead to a decline in the population of these first Metazoans, sponges had not said their last word. Even today, they can be found in every corner of our oceans, so they have a few trump cards to play. They have witnessed so many events in our history, so many evolutions, upheavals, changes, and renewals. This sponge enables us to enter the new world of eukaryotes. Speaking of renewal and upheaval, in a few million years' time, we'll be plunging into a new temporal space, the one that closes the Neoproterozoic and therefore the entire Proterozoic. This is the Ediacaran. Despite all the difficulties we've already mentioned, climate change, atmospheric upheavals, rising oxygen levels, volcanic eruptions, global glaciation of the Earth, plate movements, and the breakup of the single continent Rodinia, life goes on. It will even grow and develop on an insane scale. This was the beginning of the Cambrian period, when life really took off on our planet. Although not yet as rich and diverse as it would be in the following period, we can already see the promising beginnings. The term Ediacaran refers to the hills of Ediacara, located in Australia 650 kilometers or 400 miles from Adelaide, a coastal city in the south of the island. It is on these very hills that some exceptional fossils will be found. Fossils of the oldest known multicellular organisms. The creatures we're about to see are quite different in form from anything we've seen before. They approach animal or plant morphologies as we understand them today. If we're still a long way from modern biodiversity, the richness of the fauna. Let's plunge the Australian hill again under the waters of the globe to return to 635 million years ago. Observe the Ediacaran fauna as it unfolds before your eyes. It's nothing like what we've seen so far. We owe this discovery to Reginald Sprigg. However, at the time of its discovery, the world was not yet aware of its importance or its impact on our knowledge of prehistoric flora and fauna. In 1946, he found jellyfish fossils in this part of South Australia, in the Ediacara Hills of the Flinders Ranges. These fossils are in a layer very close to the Cambrian, so the scientific community initially thought they were organisms that lived during this geological period. In the late 1940s, it was difficult to imagine, let alone accept, that such life forms were conceivable before the Cambrian. Almost 10 years later, in 1957, another discovery, that of Charnia found in Great Britain, reawakened doubts. The fossils did indeed seem close to the Cambrian layer, but far enough away to belong to another era. This time, the possibility that the Precambrian might have harbored life is being considered much more seriously. For the record, Charnia masoni was discovered by Roger Mason when he was just 15. During a climbing session with friends in Charnwood Forest, he noticed a rather unusual fossil. He had the idea of making a rubbing of the rock, a bit like drawing the imprint of a coin with a pencil. He took the rubbing to his father, who in turn showed it to geologist Trevor Ford. This discovery must have sparked a vocation. The young man would become a professor of petrology
interested in the mechanisms behind the formation or transformation of rocks. Let's return to 1957 and the discovery of Charnia. It challenged certain beliefs, even if there was still room for doubt. And then finally, around 1959, thanks to slightly more precise dating methods, another paleontologist studying Australian geology, Martin Glassner, made the connection between species found in England and others in Australia or Newfoundland in Canada. The fact that these organisms had lived in a Precambrian period was no longer in doubt. Martin Glassner devoted a large part of his career as a paleontologist and geologist to the study of Precambrian life, particularly the Ediacaran fauna. The latter is as surprising as it is interesting and enriching. It helps us better understand the origins of the world and the evolution of living organisms. The first thing that stands out is the bilateral nature of most of these new organisms, but also their shape. Here and there we can see feathery, tubular, or even leafy shapes. We can also make out the presence of organisms reminiscent of the familiar jellyfish or coral. We're no longer dealing with simple bacterial or algal microorganisms. We can also discern organisms that are different from modern fauna, but already more evolved, like this Dickinsonia. It's rather oval in shape, flat, and has a sort of central dorsal fin. It measures around 10 centimeters. It looks like a sort of feather or long leaf, perfectly anchored in the ground. This one is undoubtedly part of the Dicksonia costata species. After so many years, it's hard to find any usable traces. Luck smiled on a few researchers, including Ilya Bobrovsky, a doctoral student at the Australian National University. Analysis of one of the specimens found revealed the presence of organized matter, notably cholesterol. This means that it is indeed an animal, since fat molecules are present. The fact that it has soft tissues does little to help the scientific community learn more about this new living organism populating our oceans. Nevertheless, a few fossils, notably those from Ilya Bobrovsky's study, have enabled us to discover that Dickinsonia could measure up to 1.40 meters or 5 feet, but that it was barely more than a millimeter thick for the flattest to a few millimeters at most for the widest. It has no mouth or anus and is attached to the seabed. Scientists therefore believe it to be a benthic animal, feeding on bacteria in the water. It grows by developing new segments like thin ribs, which run from the center to the extremities. Dickinsonia costata is quite large, almost round. This is also the case for Dickinsonia tenuis. But other Dickinsonia, such as Dickinsonia lissa, can be thinner, resembling a feather. Dickinsonia belongs to the phylum Proarticulata, which also includes other fossil animals such as Caractea and Archaeospinus. The Proarticulata phylum corresponds to the first bilaterally symmetrical animals. It's really interesting to see this evolution in the world of living things. After having known only bacteria, or small algae, organisms with a certain degree of body symmetry have now developed. Others, like Dickinsonia, adopt the same kind of morphology with a feathery or leafy appearance, like one of the iconic species of the period, Charnia. Its size is estimated at between 15 centimeters and 2 meters, or 6 feet. The Swartpuntia species can also be included in this large family of rancomorphs of the period. Each of them is more broadly integrated into the Vendobiontes group.
When we speak of Ediacaran fauna, we also use the term Vendian. Vendobiontes, or Vendozoans, here means living Vendians. Vendobiontes form a clade whose branching in the Earth's tree of life is ultimately ill-defined and difficult to link with modern groups. They are close to each other, but still far removed from what we know, and fossil remains are hard to make speak for themselves so many years later. Scientists have therefore grouped them together in this rather special clade. Let's continue our journey into this ocean to discover a new species of a completely different shape, that of Tribrachidium. Its shape is round and symmetrical with 3 lobes. The lobes are twisted into spirals around 3 hooked edges. It looks like a sort of rosette. In terms of size, Tribrachidium can reach up to 5 centimeters or 2 inches in diameter. So it remains a small seabed organism. It feeds by filtration. It directs water towards the apex of the organism, i.e. the top of the animal's conical organ. This generates small eddies, and it's this kind of trace in the sediment that we've sometimes been able to find. Charniodiscus is another seabed filter feeder. Charniodiscus is stationary, i.e. it settles on sandy bottoms and never moves. There are 2 main groups of Charniodiscus, those with short stems and wide fronds, and those with long stems and short fronds. These include Charniodiscus arboreus, Charniodiscus longus, Charniodiscus oppositus, and Charniodiscus spinosus. The interesting thing about Charniodiscus is that first and foremost it's a eukaryote. It has a nucleus surrounded by a membrane. Another important fact about Charniodiscus is that it can detect different body parts. We can see the crampon, i.e. the root-like structure that enables the animal to attach itself to its substrate, a stem and a frond, the leaf-like part. On some casts, these body parts are quite distinct from one another, and the fossil imprint is very well preserved, so it's easy to imagine what Charniodiscus might have looked like when it was alive. Difficult to classify, Charniodiscus was first thought of as a ranchiomorph, then a new clade was proposed, that of the arboreomorphs, and later that of the frondomorphs. The scientific community also considered a cnidarian, and more specifically, Pennatulae, i.e. sea feathers. While its classification is still hotly debated, one thing is certain. It has been able to develop in every corner of the globe, from Australia and Japan to the Netherlands, England's Charnwood Forest, and even Canada. I'd also like to tell you about Sprigina. It's named after its discoverer, Reginald Sprigg, whose name we mentioned earlier in connection with Charnias. If Sprigina's bilaterality is to be found, we're dealing here with a different type of living being. The footprints he has left behind can be confusing. In fact, we've had some difficulty classifying it. Was it a segmented worm, a fern leaf, another rangiomorph, or part of Charniodiscus? We can see a kind of head that we'll call a cephalon. The cephalon is formed by the first 2 segments. After the head, we can also see the segmented body. Scientists believe it to be a benthic animal, i.e. one that lived on the seafloor. Our exploration takes us to the genus Rangia, an emblematic creature of the Ediacaran. This mysterious organism has a complex morphology, reminiscent of a floating aquatic plant or a sophisticated feather. Rangia measures around 20 centimeters or 8 inches in height and has a bilateral structure organized into branching frond-like lobes. These fronds, folded and geometrically organized, seem optimized to maximize nutrient uptake from the water. Rangia probably lived attached to the marine substrate thanks to a structure called a crampon. It is difficult to determine whether Rangia was an autotrophic organism, capturing light energy through symbionts, or a heterotroph filtering suspended nutrients. Its body structure, however, suggests an adaptation to shallow marine environments, where nutrients and light are abundant. This feature places Rangia in a key ecological role, probably at the center of the earliest Ediacaran marine food chains. Acarua adami, discovered in Australia, is another fascinating fossil from this period. This tiny organism measures just 5 millimeters in diameter, but reveals some intriguing details. Acarua has pentaradial symmetry, making it a potential precursor of modern echinoderms such as starfish. Its shape is reminiscent of a small round coin, with 5 lobes arranged in a star shape around a slightly depressed center. Acarua's exact role remains unclear, but it seems plausible that it was a benthic organism, feeding on organic particles in the sediment. Its mineral structure, similar to an exoskeleton, could also have played a protective role against environmental pressures or early predators. The study of fossils, like Acarua, sheds light on the origins of multiple symmetries and complex body architectures in marine animals. Yorgia wagoneri is another particularly impressive and enigmatic creature from the Ediacaran. Yorgia measures up to 25 centimeters or 10 inches long and has a segmented flat leaf-like body, with a series of elongated plates arranged on either side of a central axis. This advanced bilateral morphology reflects a body organization that seems to indicate an active lifestyle. Unlike other, more passive Ediacaran organisms, Yorgia has fossil traces suggesting that it was able to move about on the seabed, albeit slowly. These tracks, called helminthoidognites, show a sinuous movement, suggesting that Yorgia was actively searching for food. It is likely that he fed on bacterial biofilms or other organic matter deposited on the ocean floor. With its complex body and movements, Yorgia represents an important milestone in the evolution of multicellular organisms towards more active and specialized life forms. Let's take a look at another type of organism from the Ediacaran fauna, this time with a calcareous skeleton. Its appearance in the animal kingdom favors the expansion of the very first reefs. While we can imagine how important its role was during this pivotal period in history, we unfortunately find it much harder to visualize the animal's actual form. This is Claudina. The reason it's so important to mention him on this journey into Earth's past is that Claudina are reef builders, and they played this role long before corals. It's true that when we think of reefs, we immediately think of a coral reef. Even though they are absolutely magnificent and numerous, at that time it wasn't corals that primarily played the role of sea architect, but Claudina. One of their best-known constructions today is undoubtedly that found in Oman and Namibia, fossils dating from 542 to 549 million years ago. It is known as the Nama group. The irony of this discovery is that paradoxically, the remains of this aquatic reef are to be found today in one of the world's most arid deserts, in Namibia, where not a drop of water can be found for miles around. Cloudina isn't alone in this construction. If you look closely, you'll recognize stromatolites. These are the same rocky elements we saw at the beginning of the video created by bacteria. This time, we're not here for them, but for Cloudina. We've come to admire the work of the planet's first reef builders. British and Namibian geologists made this incredible discovery in Namibia. Here we can observe the biomineralization, i.e. the production of minerals by an organism, of one of the very first creatures to develop a calcareous shell. Cloudina is a kind of living divide between soft-bodied animals and those finally supporting a rigid body. So apart from the fact that the first reefs are appearing and the ocean is taking on a new face, here we can see animals that are completely different from what we've seen in previous periods. We see here that cell differentiation and biological diversity really take hold with the development of the hard shell in these organisms from another time. It was geologist and paleontologist Preston Cloud who first studied this particular organism, hence its name Cloudina. From these early studies we know that Cloudina was one of the very first shell metazoans and that it was small in size. The fossil remains it left us as evidence show microfossils, made up of interlocking limestone cones. They are only a few millimeters in diameter and measure between 8 and 150 millimeters. Cloudinas live in groups. They have attached themselves to each other and to a fixed surface, producing a kind of natural cement that forms this solid, perfectly rigid rock structure. Many scientists have taken an interest in these stars of the ocean, but it was Professor of Carbonate Geoscience Rachel Wood and her collaborators at the University of Edinburgh, University College London, and the Geological Survey of Namibia in particular who were able to shed light on Cloudina's work and its importance to the ocean. As is the case today, scientists rightly believe that reefs form an extremely important ecosystem in the ocean. It is both a shelter from predators for many species, but also sometimes a source of nutrition, or an opportunity for symbiosis between species to double their chances of survival. One question about Cloudina remains unanswered for the time being. Every radiation, every evolution is the result of a need for survival, an adaptive result of pressure from climate, environment, or predators. The hard shell and reef construction are therefore certainly an adaptation to respond to external pressure. But what is it? One thing is certain. Cloudina, without being aware of it, was the breeding ground for an explosion of future life. As early as the following eon, we can see the extent to which species managed to grow, develop, diversify, and even adopt significant evolutionary radiations. If we were to sum up the incredible journey we've just completed in a few lines, we'd start by saying that 1 billion years ago the Earth was inhabited, contrary to what the collective imagination might believe. Nature was shy, but very much present. A world both mysterious and changing. The Precambrian, and particularly the Neoproterozoic, were the breeding ground for a burgeoning biodiversity, a pivotal period in the history of life on Earth. This moment in our planet's history, marked by profound geological and biological transformations, was the prelude to the great stages in the evolution of living organisms. 1 billion years is almost yesterday in Earth's history, but the traces left behind are still visible in the rocks and fossils we study today. Although life was only beginning to evolve during this period, it's clear that in the Neoproterozoic era, it was already undergoing radical transformations that would shape the planet's future. Just look at the many climatic, geological, and biological events that took place on Earth 1 billion years ago. The Neoproterozoic saw periods of glaciation, the formation of supercontinents, dislocations, volcanic eruptions, orogenies, and above all, the arrival of oxygen and all its consequences. Oxygen formed the Earth's protective ozone layer, but also modified the living conditions of the first aquatic creatures. And speaking of aquatic beings, what changes there were in just a few million years. Whereas life used to be merely bacterial, just algobacterial, we now see mixed-cell organisms populating the oceans. Organisms can be seen sporting a variety of shapes, including feathers. There's also a new bilaterality that wasn't present until now. The first hard-bodied animals also make their appearance, encouraging the expansion of other species and forming what can be considered the world's first oceanic reefs. These events mark the final stages of the Precambrian and set the stage for the biological and geological revolutions of the next era, the Phanerozoic. This period of history is truly the cradle of the great Cambrian explosion of life to come, but we'll see about that on our next trip. But what might the planet have looked like during the Cambrian period, which marks the beginning of the Lower Paleozoic? In the Precambrian eon, Rodinia was a megacontinent that brought together all the continental masses. Under the influence of plate tectonics, it gradually fragmented. Pieces of continental crust began to drift away across the vastness of the oceans. Shortly before the Cambrian era, two new continents appeared. Laurentia, the larger of the two, forms much of the North America we know today, minus Florida, as well as Greenland and Scotland. The second, less important, corresponds to the Siberian Shield. At the beginning of the Cambrian, a third piece of Rodinia broke off. Named Baltica, it gave rise to present-day Russia, Poland, Scandinavia, and northern Germany. The amputated Rodinia continent was renamed Gondwana. However, it was still vast, encompassing South America, Africa, Australia, Antarctica, Southern Europe, and finally China. As the three newly formed landmasses of Laurentia, Siberia, and Baltica came into being, they were subjected to the effects of plate tectonics. They moved towards and away from each other. Oceans formed while others closed. The Lapitous Ocean opened up between Laurentia and Gondwana when the supercontinent Rodinia broke up. Over millions of years, this paleo-ocean slowly expanded into the southern hemisphere, thanks to the spreading of the ocean floor in conjunction with a mid-ocean ridge located between the two continents. Around 50 million years after the opening of the Lapitous Ocean, at the end of the Cambrian, a new event gradually modified this part of the globe, reversing the opening process. A subduction zone south of Laurentia, where one oceanic lithospheric plate slipped beneath another, created an island volcanic arc. Volcanic discharges from the island arc mingled for a long time with the great thickness of sand and mud that had already accumulated between the Laurentia continent and this space riddled with volcanic islands. Sediments then accumulated in this zone, leading some 20 million years later in the Silurian to the closure of this ocean, all the more so as small continental masses also uncoupled from the Great Gondwana continent slid northwards. Together, these circumstances led to the gradual closure of Iapetus. As the insular volcanic arc moved closer to Laurentia, it eventually collided with the continental margin and began the long process of building a mountain range, the premise of the Caledonian orogeny, which would much later give rise to the Appalachians in North America and the ranges of Scotland and Scandinavia. The Cambrian began as the last ice age of the Proterozoic. The gas-gear's glaciation was coming to an end. A gradual and continuous warming of the climate led to average temperatures well above those we know today. But were the continents thus formed suitable for the development of any form of life? Although the climate seemed favorable, with average global temperatures estimated at 25 degrees Celsius or 77 degrees Fahrenheit, the continents that then occupied mainly equatorial zones were nevertheless, unlike the oceans, devoid of any signs of life. However, thanks to cyanobacteria, the first algae to appear and play a crucial role on Earth, the great oxygenation of the planet occurred, opening up the field of possibilities. Laurentia, Siberia, and Baltica thus enjoyed a tropical climate. Gondwana, located near the polar zone, experienced relatively cold temperatures, but without a land cover of ice. The intertropical zone, on the other hand, was more arid. The atmosphere contained 20% oxygen and 0.5% carbon dioxide, but the ozone layer was far too thin to protect the surface continents. Relatively exposed to ultraviolet radiation, they were unable to support any form of life. With no plant cover whatsoever, the continent surfaces were totally barren, desert-like, and arid. Only the movement of tectonic plates and intense erosion eventually altered the appearance of these lands, which consisted of rocky peaks or barren, cracked plains. The shallow oceans, on the other hand, were able to take full advantage of these conditions to develop the life already present, thanks to their warm waters. At the beginning of the period, only unicellular, then multicellular organisms populated the submarine space. Prokaryotes, single-celled microorganisms with no nucleus or nuclear membrane, such as bacteria and archaea, were found. Then, in addition to the many cyanobacteria, came the eukaryotes, which had appeared during the Proterozoic eon. But we'll see later how climatic conditions played a major role in the evolution of these species over the 56 million years that make up the Cambrian period. Some 600 million years ago, towards the end of the Proterozoic eon, just before the Cambrian era, the Ediacaran fauna, composed of soft-bodied, leaf and tube-shaped organisms, developed for almost 56 million years before suddenly disappearing. The reasons for this sudden disappearance remain an unsolved mystery to this day. However, traces of this fauna have been found all over the world. It was made up of primitive representatives of younger groups, essentially the Cnidarian phylum, soft and medusoid corals, annelids, segmented worms, and arthropods. One of the few survivors of this short period is the jellyfish. But the event that followed was of such importance that it marked the beginning of a new era, the Cambrian. The Cambrian is the era that marks the beginning of fossiliferous times. Following the last ice age of the Proterozoic, the planet underwent a transmutation. Temperatures were much milder, and an unprecedented extension of the epicontinental seas allowed underwater life to develop at an unprecedented rate, but not only in terms of quantity. On a geological timescale, new anatomies appeared on such a scale that we speak of a Cambrian explosion. This was the first evolutionary event of its kind, marking a decisive turning point in the evolution of life on Earth. Some authors have even dubbed it the zoological Big Bang. Most of today's major metazoan phyla appeared between 541 and 505 million years ago. Although some of these multicellular animals have since disappeared, this Cambrian explosion was the initiator of a great diversification of animal, plant, and bacterial classes and species. Living organisms acquired shells, carapaces, and even skeletons, leaving their mark on fossils. Most of these were soft-bodied animals, such as worms and sponges, but the first arthropods, distant ancestors of crustaceans and insects, also appeared. There are also traces of the cephalopods of the future, including the octopus. The rapid emergence of new animal varieties, particularly bilaterians, made ecosystems much more complex than they had been before, when they were populated by relatively simple organisms, as witnessed by the Ediacaran population. Completely new ecological interactions, such as predation, appeared in new marine environments and habitats. Some so-called benthic species lived on the seabed, or even in the sediment covering it. Others, on the other hand, evolved in the aquatic environment. These are known as tectonic animals. The causes of the Cambrian explosion are still not really known. However, several hypotheses have been put forward, some of which are linked to one another. The first is based on an increase in dissolved oxygen in the oceans following the end of the last ice age. There may also have been an increase in the production of phosphate and nitrate ions, essentially for primary photosynthetic production, and enabling phytoplankton development and mineralization of hard parts, such as shells and sclerites. Changes in the food chain, inducing competition between prey and predators, may have favored co-evolutionary mechanisms between different species. As a result, new and vital defense strategies, such as carapaces, shells, and spines, would have developed, offering primordial protection against predators, themselves finely equipped with visual elements. And then there's the question of whether small genetic changes may have occurred accidentally during the embryonic development of certain species. You're probably wondering, and rightly so, about the evidence that has been found from this period. It is indeed legitimate to wonder how fossilized traces of these microorganisms, which moreover lived exclusively on the seabed, can be discovered. If it's hard enough to bring to light the fossilized remains of dinosaurs that appeared almost 300 million years later, what stigmata can be exploited? Fortunately, a large part of the Lapitous Ocean seabed has been preserved. As plate tectonics continually shaped the Earth's crust, surfaces in the ocean depths were raised to mountain slopes. This explosion of life left many fossils that can be found all over the globe. Traces of the Cambrian period can be found all over the world, on every continent. However, current knowledge of life during the Cambrian is based on the study of the lager state, the storage site still available, where paleontologists are continuing their research. The Cambrian is also well represented in France. Numerous fossils have been discovered in the southwestern Massif Central, more precisely in the Montagne Noire, but also in the Pyrenees, Normandy, the Cevennes, in small outcrops in the Pays de la Loire, and finally in the Ardennes. The first Cambrian fossils to be discovered in France date back to 1888. Trilobite debris was identified in the Montagne Noire, where the stratigraphy subsequently proved to be particularly representative of the Cambrian era. The Burgess Shale is one of the world's most remarkable storage sites. Discovered on August 30th, 1909, by paleontologist Charles Doolittle Walcott, they are located near Mount Burgess, high in the Canadian Rockies, in the heart of Yoho National Park. It's a black shale deposit where fossils, most of them around 505 million years old, bear witness to the end of the Cambrian explosion. Shale is a type of sedimentary rock composed of clay and silt. Often very friable, these rocks reveal the fossilized remains of surprising, even disconcerting creatures. As we noted earlier, the mountains of the Canadian Rockies were once the seabed of the Lapitous Ocean. Sediments were deposited in the deep waters in the form of mudflows, capturing the animals present in this area. The scarcity of oxygen slowed their decomposition, so over time they were transformed into black, thread-like fossils. Skeletal elements from the Cambrian period are generally small in size. They come from small-shelled fauna. Different parts of mineralized skeletons are studied, such as sclerites, the calcareous part included in the tissues of certain corals, spicules, the calcareous or siliceous constituents, forming the skeleton of sponges, tubes, or shells. These elements probably belong to several different types of animal. But what is most remarkable about the Burgess fauna is the appearance of specific internal and external organs. At last, the animals were equipped with legs, visual attributes, a mouth, digestive system, antennae, and many other special features. To date, almost 150 species of animals, algae, and bacteria have been recorded in Walcott's quarry. Thousands of specimens are divided into several collections, enabling scientists to study the ecosystem as a whole. Quantitative statistics are now possible for the first time, thanks to the sheer quantity of fossils. Researchers estimate that almost 98% of the fossils on this site are those of soft-bodied organisms. The site's unique preservation conditions make it exceptional. Indeed, in most Cambrian marine deposits worldwide, this type of fossil is absent, not because they weren't there, but because they were not preserved in the right conditions. The Burgess community is essentially made up of animals. A few species of green algae and red algae have been recorded, as well as microbial colonies. But the groups most representative of this new environment are undoubtedly the arthropods, those small animals with articulated legs that molt, and the porifers, i.e. the sponges. Without further ado, let's take a look at the species that populated this paleo-ocean, then called Iapetus. Let's start with the most widespread animals, the benthics, i.e. those living in or near the seabed. Canodaspis perfecta is one of the ancestors of the arthropods found today in the form of crustaceans, insects, and arachnids. This specimen, which also left traces in China, measured from 8 to 52 millimeters in length. Its body was partially covered by a carapace and ended in a segmented tail, with a telson at the tip, which itself had a double spiny projection pointing backwards. Its bivalve carapace was surmounted by 2 eyes, between which a spinal column began. It was equipped with 1 pair of short antennae and another, longer pair, whose function was probably olfactory. 2 pairs of legs were located at the level of its head, all equipped with a terminal claw. More than a dozen segments made up its body. The thoracic part was equipped with 8 pairs of associated biramous legs, similarly equipped with claws, while its posterior abdomen was devoid of them. Legs or appendages are said to be biramous when they have both gills and locomotor appendages. Canodaspis perfecta walked along the seabed, stirring up mud with its feet to find its food. Once the food was found, it used its pair of mandibles and maxillae to feed. Among the animals that inhabited the seabed, many species with elongated bodies resembling today's worms lived on the seabed or in the sediment that covered it. Others had a particular morphology that enabled them to swim actively. These elongated animals belong to the category of annelids. 5 species have been recorded in the Burgess Shale, including Piranacheta, which preferred a sedimentary environment, and Canadia spinosa, which swam with ocean currents. Let's take a look at the Canadia spinosa. This annelid worm measured an average of 3 centimeters or 1 inch long, and could reach up to 4.5 centimeters or 2 inches in length. The main characteristic of this animal is the numerous rigid bristles that extend from its dorsal branches all the way down its back. This feature is typical of polychaete worms. On their distinctive segmented structure, each segment carries a pair of conspicuous lateral appendages called parapodia, used primarily for locomotion. On these parapodia, tufts of a variable number of bristles, the chaetae, facilitate their movement in the aquatic environment. The Piranacheta, on the other hand, preferred contact with sediments. This tiny, thread-like hairworm takes its name from the Greek words peroni, meaning needle, and kate, meaning long hair, in reference to the bristles that cover it. This worm grew to between 1 and 2 centimeters or 1 inch in length, with a body just 1 millimeter wide without the bristles. Its body consisted of around 25 segments, each equipped with a pair of parapodia. This carnivorous, even detritivorous animal had a straight intestine running the length of its body. Its cephalic region was equipped with a pair of tentacles. This worm was endobenthic and epibenthic, which means it could move both on sediments and within them. Its bristles, very useful for its movements, probably helped it to bury itself in the sediment, both to hide and to search for food. But a much larger worm was discovered in the astonishing Burgess fauna. This is the capinitator, Praetermissus, a worm that proved to be a formidable predator during the Cambrian period. Considered a monster, it measured 11 centimeters or 4 inches, and its broad head was lined with 50 hooks. Nicknamed a Sagittarian worm because of its arrow-like shape, it is described as a chatognath. The name chatognate means jaw hair. In fact, it was its numerous movable hooks that enabled it to capture its prey. This worm is considered a branch of marine predators. Even today, this type of worm can be found in all seas. Although they haven't changed much, they are now often only a few millimeters long. Yet nestled among the plankton, it behaves like a fearsome predator, its hooks claiming numerous victims among the larvae of fish and crustaceans. The seabed was also occupied by brachiopods, animals that fed on suspended particles and whose bodies were housed in bivalve shells. Generally, they attached themselves to a surface on the seabed or to another larger organism by means of their peduncle, a cylindrical, flexible organ. Micromitra burgessensis was one of these brachiopods, whose maximum size was 10 millimeters. Its name comes from the Greek and means little turban. It was the most equipped of the brachiopods found at the Burgess site. It had a mineralized shell. This was adorned with pronounced striations of growth and fine raised lines raising out from the hinge across the entire shell, creating small diamond-shaped patterns on the top. Its valves were subcircular, while its hinge was practically straight. This specimen was also adorned with long, thin bristles that extended well beyond the margins of its shell. These were attached to the edge of the mantle, along the dorsal and ventral valves. Some of these specimens have been found fossilized while attached to the spicules of a variety of sponge, the Piranha sponge, confirming its benthic lifestyle. In the waters of this ocean, animals were actively swimming. This was particularly true of the chordates, animals with dorsal ropes and dorsal spinal cords. Pikaea gracilens, one of the fossils found in the Burgess Shale, undoubtedly represents the most primitive form of chordate. At the time, this ancestor of vertebrates only looked like a worm. However, it has been demonstrated that this animal was equipped with myomeres, the muscles of vertebrates. It measured around 5 centimeters or 2 inches in length. Its elongated body, with a head at the front, gave it the appearance of an eel. Its body, flattened at the sides, suggests that it had a ventral fin located towards the rear. Although this animal spent a lot of time on the seabed in search of food, looking for organic matter, such as snails or sea urchins, it could probably swim at will. One of the arthropods had 2 pedunculated eyes. This is the Sydneyea. With a maximum size of 160 millimeters or 6 inches, it had a convex, cephalic shield, short but wide and subrectangular in frontal view. The 2 lateral corners were notched to accommodate an antenna and eye stalk on either side. Its 2 hemispherical, highly reflective eyes pointed above and behind each antenna. Its thorax was composed of 9 segments, the middle ones being wider. The first 4 thoracic segments had appendages with a large base and 8 lighter ones ending in a sharp claw. The next 5 thoracic segments had identical appendages, but these were associated with branches of filaments, forming what could be described as a wing. Finally, its abdomen was made up of 3 much thinner segments and ended in a triangular telson, accompanied by a pair of large articulated paddles, forming a caudal fan. This carnivore swam and walked on the seabed with the help of its 4 anterior pairs of thoracic appendages, while the filamentous branches of its 5 posterior pairs enabled it to propel itself through the water column. These same filaments may even have participated in the animal's breathing, acting as gills. Its spiny basal coxae helped it to crush food and transport it to its mouth. Its eyes and antennae helped it to move above the seabed in search of its prey, which it had to grasp and then crush with its front appendages. Another primitive arthropod had not 2 but 5 eyes. This was Opabinia regulus. Because of its unusual morphology, including a strange frontal proboscis, it is one of the iconic fossils of the Burgess fauna. Its body, whose maximum size was 10.1 centimeters or 4 inches, featured gills and lateral lobes repeated in series, as well as a generously proportioned caudal fan. Its complete body, measured without its proboscis, was between 4.3 and 7 centimeters, or 2 inches. On the anterior margin of its rounded head were 5 prominent eyes. They were bulbous in shape, surmounted by short peduncles. Its ring proboscis was 4 times the size of its head. Extremely flexible, it ended in a pair of opposing pincers, each with 5 or 6 spines. The ventral mouth was directed backwards. Its trunk was composed of 15 segments, each housing a pair of lateral lobes, themselves bearing gill structures in the form of lamellae. The trunk was followed by a caudal fan with 3 pairs of upward-facing fins. This carnivorous animal swam thanks to the waves of undulations produced by its lateral lobes, which acted as propellers. Its caudal fan, like a rudder, helped it to steer through the water column. Its flexible proboscis and pair of distal pincers were invaluable for catching soft foods and bringing them to its ventral mouth. The seabed was certainly colored by echinoderms. Echinoderms are a distinct group of organisms characterized by a mineralized skeleton made up of several elements with pentameric symmetry. We find this structure today in starfish, whose bodies contain 5 identical parts, radiating from a central point. Naturally, carnivorous animals were fed on mollusks in large numbers. Of the 5 species discovered in the Burgess Shale, only one had a mineralized shell, the Scanella. Sponges also populated the ocean floor. They are among the most primitive animals known to the oceans. Their bodies had no real tissues. Many of these species had a skeleton made up of a mesh of fine mineral rods known as spicules. These demosponges were benthic filter feeders. They therefore belong to the phylum Poriferae. Specimens of several species of the Voxia genus have been found in the Burgess Shale, including Voxia gracilenta. This sponge, very common on this site, measured a maximum of 8 centimeters. Simple and unbranched, or with more complex structures, each of its branches was almost cylindrical, forming a highly accentuated cone with a simple central cavity with a concave or flat opening. To feed, these sessile creatures had no other means than to continually filter water through the channels in their walls in order to retain the particles of organic matter then present. Other species, with variations in skeletal elements and branch shape, were also widespread, such as Voxia bullula and Voxia densa. These could reach up to 15 centimeters or 6 inches in height. Anchored to the seabed, they provided perfect shelter for epibenthic fauna, whose habitat was essentially the seabed. But the best-known sponge in the Burgess Shale is undoubtedly the Hazelia palmata. It is assigned to the upper group of demosponges of the order Monaxidina. The Hazelia genus is highly diversified. It includes species of various morphologies. Some were large and cup-shaped, such as Hazelia palmata, Hazelia crateria, and Hazelia luteria. Others were elongated and conical, such as Hazelia conferta, Hazelia grandis, and Hazelia obscura. There were also some particularly branched species, such as Hazelia delicutala, and others in the form of nodules or lobes, such as Hazelia lobata and Hazelia nodulifera. However, despite the considerable diversity of their general forms, these species all had the same microstructure. They were thin-walled and composed of small spicules densely grouped together in a mesh-like structure that opened outwards. Hazelia palmata, which measured up to 15 centimeters or 6 inches, was distinguished by its open, shield-like shape and numerous clusters of prominent radiating spicules. Among the arthropods active on the seabed alongside these sponges was the Naroya, often compared to trilobites. This marine animal, at most 4 centimeters or 2 inches long, had 2 ovoid dorsal shields with a convex axial region. It therefore had a cephalic shield and an elongated shield protecting the rest of its body. 2 long, articulated antennae protruded from the anterior shield. Behind the antennae were 4 pairs of cephalic appendages, with a further 14 pairs on the trunk. Each of these appendages was segmented and bi-branched. One part formed the locomotor branch, divided into 7 segments and thus perfectly adapted to walking. The other part was a filamentous branch, consisting of a fine shaft from which numerous lamellae sprang. These appendages ended in a large spiny plate. Thanks to its antennae, which were probably sensory, the Naroya was able to locate its food, which it brought to its mouth using the spiny plate at the base of its appendages. It could, however, take short swims, using its filamentous gills to propel it through the aquatic environment. If this carnivore was a scavenger, even a predator, the scars found on the carapace of certain specimens prove that it was also attacked by larger predators. Finally, a carnivore with a tubular carapace completes the list of arthropods. This is the Oderia alata. Most of this animal's body was enveloped by an imposing carapace, the midline of which was visible along the dorsal midline. These two united valves on the ventral part make this specimen very special, its carapace forming an open tube at the front and rear of the animal. Its head, which protruded from the tube, had a small anterior plate containing large spherical eyes surmounted by short peduncles. Its body consisted of around 47 segments, each with a pair of appendages. Those of the first two segments took the form of slender segmented branches adapted to walking. The other appendages were bibranched and divided into an inner branch with a large branched basal spine and an outer branch with filamentous lamellae. Its tail, or telson, consisted of 3 fins extending laterally and vertically. This predator's ventral appendages, blocked by its tubular carapace, probably made it difficult for it to walk on the seabed. Nevertheless, the Oderia was a mobile animal. It could plausibly swim in the water column, thanks to the undulation of its internal branches and biramid appendages. Like a suction pipe, it filtered aquatic organisms that entered at the front and exited at the rear of its carapace. Its large telson, very useful when on the move, helped it to steer, and why not, to manage rolling or braking when swimming. As you can see, this paleo-ocean was teeming with life, even if sea monsters were only small in size at the time. On a zoological scale, the Cambrian explosion led to an unprecedented diversification of animal species. Above all, it marked the emergence of modern ecosystems. The biodiversity of marine life during the Cambrian is also perfectly illustrated in a region of southwest China. Various sites in Chengjiang, located in Yunnan province, are renowned for the quality of preservation of the fossils discovered, including their soft parts. The Chengjiang fauna came after the small shell fauna that marked the beginning of the Cambrian period. New life forms appeared at this time, some 520 million years ago. One of the sites, Maotianshan Hill, has been a UNESCO World Heritage Site since 2012. It was on this hill that this lager state was discovered by Dr. Qian Guang Hao of the Nanjing Institute of Geology and Paleontology in 1984. The Chengjiang fossils comprise 16 phyla, over 170 genera, and more than 200 different species. They mark the first appearance of the majority of animal phyla existing during the Phanerozoic, many of which still populate our planet. The first specimens of algae, sponges, brachiopods, arthropods, chordates, and echinoderms have been found. But the long list doesn't end there. Hallucigenia is one of the most studied specimens. This animal, then considered a polychaete worm of the Canadia genus, has been extremely well preserved, providing experts with precious anatomical details. It had an oval-shaped head, attached to its cylindrical body by a constriction giving it a neck. Measuring 22 millimeters or 1 inch in length, it had 7 pairs of dorsal spines and 7 pairs of legs, with small claws at the ends. Today, it is classified as a lobopod. One of the most popular inhabitants of the Changjiang fauna is a numerous arthropod, some specimens of which are in an excellent state of preservation. This is the Leoncholia illicabrosa. It can be recognized by its elongated segmented body, its biramid appendages, and above all, its 2 large head appendages, each bearing 3 flagellas about 2 centimeters or 1 inch long. Another common animal has revealed numerous anatomical details. This is Eurydichia intermedia, a trilobite that revealed fine uniramate antennae on the front of its head, large crescent-shaped eyes framing a rounded area extended by 2 long spines. Its posterior part ended in a long thorn-like tail. But the most famous fossil in the Changjiang fauna is undoubtedly the Mylocunmingia fengioa. It represents the oldest known vertebrate. At around 2 centimeters or 1 inch in length, it is a small primitive fish. Its head was distinct from its trunk. It had 5 to 6 gills. Its trunk was equipped with a dorsal and ventral fin, probably twinned. The thorax had 25 V-shaped segments, with the tip turned backwards. While the location of its mouth is not yet clear, it did have a pharynx, as well as a digestive tract, that extended to the tip of its tail. Another species stands out in the Changjiang fauna, this time for its size. This is the Anomalocaris sauron. This predator of the now extinct Anomalocaridae family, also known as the strange shrimp, could measure over 1 meter in length, which is quite exceptional and even spectacular for this period of animal history. Its anterior part was equipped with a pair of large segmented prehensile appendages, edged with spines. Its head was surmounted by 2 large pedunculated eyes, while its underside featured a characteristic ringed mouth. Its segmented body, composed of 11 pairs of lobes, probably made it a very good swimmer. Thus equipped, it must have had no difficulty in feeding on trilobites, which it hunted with a sharp eye. In this complex ecosystem, scientists deduced that over 55% of species were arthropods, 10% were sponges. In addition, more than 10% are still of uncertain form. Most of the fauna lived on the ocean floor. Indeed, few of the specimens we have just observed were pelagic, as their structure was not equipped with elements that would enable them to swim, even passively. Feeding habits were equally varied. There were filter feeders and fearsome predators. While some of these animals were content to scavenge from the sediment, others were active hunters. At the Changjiang site, the Cambrian explosion is anything but a legend. The diversification of life is well represented, notably with the appearance of numerous phyla previously unheard of. While many descendants emerged within a single phylum, some endured while others died out in later geological times. Whatever the case, this period witnessed the emergence of all the complex forms of animal life as we know it today. In the lower Cambrian era, during the first 2 series of the Terranuvian and Series 2, a short period stood out, giving rise to the Tomotian fauna, named after the Siberian town of Tomot. This fauna appeared during the Cambrian explosion 530 million years ago, but lasted only a few million years. Yet, like the Ediacara fauna, it is similarly recognized around the globe. The Tomotian fauna is also often referred to as the small-shelled fauna, and for good reason. While it contains some organisms that look modern for their time, most of its representatives are formed of tiny blades, tubes, needles, caps, or domes. For paleontologists, the nature of this small-shelled fauna remains a mystery. Are they simply scattered fragments of the very first types of shells, still imperfectly formed by unrecognizable organisms? Or are they remnants of pieces of shell that covered previously known but unidentified animals whose construction improved over time? Or do these strange finds correspond to unique organisms that appeared early before spontaneously disappearing? Until recently, the Tomotian fauna was considered to be the first fauna with hard parts. But recent discoveries of organisms with mineralized skeletons have shown the opposite to be true, the latter being found in the stratified layers of the late Precambrian and early Cambrian. Nevertheless, the Tomotian fauna is also important for another reason. It marks the appearance of a group of organisms that most probably belong to the Porifera phylum, that of the sponges, the archaeocyaths. Although this phylum disappeared at the end of the Cambrian, archaeocyaths were the very first bioconstructors in association with calcimicrobes, calcifying microbial communities. They were able to generate organic masses measuring 1 to 2 meters in height and a few meters in diameter. These calcified sponges would then adorn the seabed like never before. These massive organisms were the precursors of the complex reef ecosystem that developed a few million years later, toward the end of the Ordovician period. All that remains of the Tomotian fauna is the sponge category. If organisms were able to develop on such a scale during the Cambrian, they were not the only ones. We have already observed a superpredator known as Anomalocaris. This strange, extraordinarily large shrimp, sometimes more than a meter long, wasn't the only one to rain terror on the ocean floor. A recent discovery, published in June 2022, mentions the existence of another giant arthropod, belonging to the radiodont group. This is the Titanocoris gainaceae. Its remains have just been found in the Burgess Shale fossil formation in British Columbia's Kootenay National Park. Its name, a reference to the word Titan, is self-explanatory and testifies to the exceptional size of this animal. The suffix coris means helmet in Greek. At around half a meter in length, the size of this animal was absolutely breathtaking at that time in animal history. While today it may seem almost insignificant, it's worth remembering that at the same period, the vast majority of living creatures were no more than a fifth of this size, with the exception of the Anomalocaris sauron we met earlier. Like its herded cousins, a subgroup of radiodonts, Titanocoris gainaceae was characterized by an exceptionally long head, covered by a 3-part carapace of multiple shapes. The head of this specimen was so disproportionately elongated in relation to the rest of the body that some refer to it as a swimming head. Its mouth was shaped like a cone, with several radiating plates lined with teeth. Stemmed eyes with several facets crowned the mouth. A pair of long frontal appendages, ending in claws and pointing backwards, flanked its head. Finally, its trunk, made up of multiple flaps that were certainly intended to facilitate swimming, supported gills and ended in a front spine. This colossus, whose outer carapace was wider and thinner than that of the average radiodon, must have swum close to the seabed. Adapted to life close to the ground, it was most likely one of the most dangerous predators the oceans could count on during the Cambrian era. Smaller radiodonts, on the other hand, although with similar physical characteristics, were filter feeders. This probably explains the possible cohabitation of these two radiodont varieties, with Titanochorus gainesi certainly preferring to devour larger prey than its cousins. The study of exceptional faunas such as those of Chengjiang, Burgess, and many others, together with abundant paleontological data, allow us to assert that a complex marine ecosystem newly emerged at the beginning of the Cambrian. While the animal world preceding the Cambrian explosion was already highly diversified, comprising several phyla each, with different strategies for exploiting the environment, the anatomical organization of specimens was still relatively simple. During the Cambrian, we witnessed not only an unprecedented proliferation of living organisms, but above all, the emergence of new anatomical and functional formations far more complex than ever before. From a sensory point of view, evolution is marked by the appearance of eye organs and antennae. Organisms are equipped with gills and a circulatory system, demonstrating that they had a respiratory system. In terms of feeding, complex digestive systems emerged. Some animals possess systems for capturing food particles, and in the case of predators, even prehensile organs. Finally, in terms of locomotion, more or less numerous appendages and flotation organs also appeared. Not to be forgotten are the prominent appendages found in arthropods, some of which have given rise to groups such as the crustaceans. These new anatomical peculiarities are accompanied by an increasingly complex marine ecosystem. Animals are no longer simple unicellular organisms like prokaryotes or eukaryotes, or even multicellular like certain myxobacteria. They are now endowed with a variety of specific organs, depending on which phylum they belong to. The discovery of organisms of different designs indicates the existence of an already highly structured food chain. Indeed, we find priapulan worms inside the sediment, numerous arthropods that lived on the seabed, and even swimming predators such as the fearsome Anomalocaris. But the anatomy of these organisms, miraculously preserved in the fossils, isn't the only clue to learning more about these newly appeared animals. In some deposits, scientists have been able to analyze the stomach contents and coprolites of certain specimens. Observations of the fossilized food in the stomach, and even of the excrement, still present in the intestines, has provided relatively precise indications of the diet of some of these animals. In this way, it has been possible to establish that certain species fed on other animal varieties. These stomach contents provide direct evidence of animal interactions within the food chain, In the Burgess Shale, several organic and skeletal elements have been found preserved inside the stomach or intestine of some of the animals studied. The priapulan worm, Otoya, seemed to feed on hyaliths, those enigmatic horn-shelled organisms. Several aligned shells were identified in its digestive tract. The arthropod, Sydneia, on the other hand, had a varied diet. Numerous fragments of hyaliths, trilobites, and bradorids, small bivalve arthropods, were found in the digestive tract of this carnivorous predator, which measured between 5 and 16 centimeters, or 5 inches in length. But scientists weren't content to simply observe the digestive tracts of certain species. Among the fossils examined, some could be coprolites. These potential fossil excrements come in different shapes. Some, elliptical and composed of aggregates of skeletal elements, belong to the Chengjiang fauna. They turn out to contain mostly fragments of waptids and bradorids, the small bivalve arthropods that populated the seabed. These are probably excrements produced by one of the largest predators, the Anomalocaris, which measured almost a meter in length. Other clusters discovered in the form of a ribbon and consisting almost entirely of hyaliths are undoubtedly the remains of carnivorous priapulan worms. These observations suggest that endobenthic predators, such as priapulans, were not the only ones to exploit the water sediment interface. Arthropods, which moved along the bottom, and Anomalocarids, which moved through the water column, shared the same hunting grounds. In addition, traces of attacks and perforations were found on the carapace of some trilobites. Surely inflicted by Anomalocaridids, they testify to the bloodthirsty atmosphere that reigned on the seabed. Fractures and traces of regeneration, certainly due to predation, have also been noted on the shells of an Australian Lower Cambrian mollusk, Marocella. These small organisms, with biomineralized exoskeletons, were similarly subjected to constant predation. The Cambrian was thus marked by the appearance of the first ecosystems with a complex trophic structure, particularly in the animal sphere. Biological interactions, such as predator-prey relationships, are evident. New ecological niches, both benthic and pelagic, were occupied by a variety of predators, including scavengers, detritus feeders, and suspension feeders. Although the pelagic domain was probably not entirely occupied by swimming species during the Lower Cambrian, the concentration of animals in hyperbenthic environments close to the bottom is obvious. This was certainly the first step towards colonization of the water column, followed by the emergence of pelagic food chains. But what were the factors that triggered such an evolution? The establishment of this entirely new ecosystem is based on a number of decisive events and innovations. In the early stages of Metazoan evolution, climate, water, chemistry, and oxygen were most likely important environmental factors. But the acquisition by some species of a more complex nervous system, novel visual organs, and improved motor skills will certainly have enabled the introduction of new selective pressures such as predation. The light switch theory suggests that the introduction of vision into early Cambrian aquatic communities was the main trigger for this ecological renewal. This would have generated a completely new mode of animal interaction and triggered active predation. A cascade of feedback effects followed, such as defensive responses from certain prey, with the appearance of exoskeletons, biomineralization, and even new behaviors. Crucial improvements in the functioning of the nervous system in early metazoans may have led to the emergence of new vital functions such as vision, limb coordination, locomotion, and even active predation. These new abilities undeniably modified the behavior of fauna, considerably changing ecological rules. Other hypotheses have suggested that major changes in phytoplankton composition took place during the transition from Precambrian to Cambrian, enabling an explosion in animal radiation. An increase in atmospheric oxygen could also have made possible the physical evolution of large animals with higher metabolisms. However, animal biomineralization during this same period is the most important event recorded. Its repercussions on the functioning of early ecosystems can only have been extremely significant. While the Cambrian period saw an unprecedented boom in the development of life, a first extinction followed the Cambrian explosion, which seems to have peaked between 520 and 540 million years ago. But a significant event occurred around 485 million years ago. During this first period of the Paleozoic era, multicellular beings underwent one of the many biological crises that would affect all life forms in subsequent periods. Over 85% of the biosphere's species disappeared. So what happened on the planet to have such an impact on life? While it is acknowledged that 99% of the species that have ever existed on our planet eventually became extinct, the vast majority did so as part of a process of normal species extinction, linked to the limited duration of their biological existence. However, the Cambrian period saw the sudden disappearance of certain species, as did many others that punctuated the development of life on Earth. Some researchers suggest that at the beginning of the Middle Cambrian, the climate underwent rapid oscillations between hot and cold. These climatic changes would have been so rapid that many species would not have had time to adapt, and consequently to survive. A great global cooling and variations in sea level would have modified the terrestrial environment, considerably impacting living conditions on the planet. But what is their theory based on? Geoscientists have successfully dated lavas from the Kalkarindi volcanic province in Australia, as well as over 2 million square kilometers or 770,000 square miles of magmatic rock located in the Northern Territory of Western Australia. Their findings attest to the fact that these lava emissions, which occurred very rapidly, took place at the same time, around 510 million years ago. These events correspond well with the mass extinction of the early Middle Cambrian. Moreover, chemical analysis of these basalts shows that they are relatively low in sulfur dioxide. However, following a major volcanic eruption, an increase in atmospheric sulfur dioxide undeniably causes a temporary cooling of the climate. Could there have been a new period of glaciation, which, although less severe than the Veringer glaciation that ended the Proterozoic eon, would have decimated much of the nascent flora and fauna? Another hypothesis is that the oceans and atmosphere were depleted of oxygen and enriched with carbon dioxide. This global greenhouse effect would have caused global warming. But how did this greenhouse effect come about? Before the Cambrian explosion, the seabed was covered with organic matter that had accumulated over time, forming a thick, dense layer. According to some scientists, the rapid appearance of Cambrian fauna disturbed the tranquil equilibrium of the seabed. The animals, then in great numbers, would have stirred up all these organic layers. By fragmenting and decomposing the organic matter in the soil, the worms and arthropods triggered a mechanism that consumed oxygen and released carbon dioxide. As a result, this explosion of life became somewhat self-sabotaging, depleting oxygen not only from the oceans, but also from the atmosphere. As a result, the anoxic waters decimated the Cambrian fauna on a massive scale, leading to the extinction of numerous species of trilobites. However, geological records show that some species managed to survive, their bodies having adapted to this low oxygen environment. Finally, an extraterrestrial cause, such as a meteorite impact or the supernova explosion of a nearby star, producing a lethally powerful gamma-ray burst, could be the ultimate explanation. In just 10 seconds, the atmospheric ozone layer would have been destroyed, no longer protecting oceanic plankton from the devastating ultraviolet rays that were at the origin of the food chains then in place. A new ice age would then have slowly set in, covering the supercontinent Gondwana at the South Pole with an immense ice cap. With sea levels lowered and ocean circulation slowed, low oxygen levels would have led to much more difficult living conditions. The Cambrian era thus came to an end with a massive biological extinction, known as the Cambrian Ordovician extinction. Brachiopods, conodonts, and trilobites were the animals that experienced the greatest reductions in species numbers. But as with every event of this kind, the surviving species take over the ecological niches left vacant. Nature shows unexpected resilience, and despite the unattractive environment, life continues to thrive. In a much calmer ocean, life returns to normal. Survivors multiply, and new species appear. At this precise moment in its evolution, planet Earth seems to be in full gestation. Will life, which first appeared in an aquatic environment, soon spread to dry land? If we can confirm that this will indeed be the case, will this spectacular evolution of species develop in the next period? For the moment, the Cambrian is giving way to the Ordovician period, a new era in which the global ocean and Earth's atmosphere cooled considerably.